Hello everyone and welcome to the DNA 10.4 release webinar. My name is Maz and with help of my colleagues Chantal Friesen and Jean-Claude Barrel, we are pleased to present and demonstrate new features and analysis capabilities which are available in this very latest version of DNA. In the last year, we released DNA 10.3. This version was very successful and presented a new approach towards both civil and geotechnical engineering applications. However, the trend in engineering workflow and associated technologies are constantly developing and advancing. Having said that, we received valuable feedback from our clients and partners for further developments in DNA. It was very important but difficult for us to be selective and blend all these important requests from the market with our company's futuristic vision to a list of developments and enhancements which are now available in DNA 10.4. What we will be highlighting today is just a tip of great efforts of my colleagues in various departments who are proud to work at DNA FEA BV and deliver the cutting-edge technology to meet your engineering challenges. No need to mention that there will be more developments in our upcoming releases, so please do not hesitate to share your ideas and requests for new developments and enhancements in the future versions of DNA. So, having said that, I would like to continue the discussion and presentation for new features in DNA 10.4. We have categorized this webinar and presentation in different parts and sections. Some slides and discussions about the pre-processing, some related to the kernel and the analysis features, and indeed some highlights for the post-processing. During the session, my colleagues will demonstrate some live demo about some of the workflows and new developments and wizards that we have in this version of DNA, and also about some technicalities, especially with respect to the design features. This session will be recorded, and after this broadcast will be available in our YouTube channel and also in our website. So we start with the features which are available in pre-processing. Here is a kind of at a glance overview on some of the features that we have. We have enhanced and improved our AutoCAD reader to handle more complex and advanced set of geometries and topologies. We incorporated additional features with respect to power solid and say syncing and incorporating that with DNA environment for modeling manipulation. We improved mapped measure to tackle more complex geometries in DNA. The incremental meshing system has been advanced and help us to optimize the required time for remeshing the model. The outstanding feature that in DNA 10.4 we deliver is automated and say the wizard type of approach towards modeling sheet pile walls and associated supporting structures. My colleague will give you a live demo, and I'm sure you're going to acknowledge the optimized workflow that we introduced in this version. Definition of the clashing shapes. This is also a very useful feature in order to say to correlate the embedded parts with the reference model elements. Definition of the nodal sets for the output say group of nodes, and indeed some sort of labeling and tags for the nodes and elements. There are many more, but these are some say the highlights. We continue the presentation at analysis level and the kernel. We have done lots of improvement, enhancement, and say the additional handling process at the material levels, load definitions, handling of the element types. So we're gonna touch bases of them in the property definitions. We enhanced the formulation for free field elements to be incorporated with the seismic and say dynamic analysis. There is a new approach towards fully handshake analysis basically is a kind of continuous analysis between the structural nonlinear analysis and strain reduction analysis. This is one of the most demanded feature that our clients are asking, because during the construction, they want to see what's the status of the stability of the structure. There is a feature called equivalent linear analysis. This analysis capability is available in Dana, but is become, available upon request of the individuals. We have one nice interactive window and environment to give you the progressive information, especially when you're performing nonlinear analysis, and a comprehensive set of solutions with respect to the design check that Chantal, my colleague from engineering department, will inform us about the added value of these features with respect to the design and model code. And towards the end of the presentation, we touch bases of new features or additional enhancement for the post-processing, such as new output items, some extension of the animations, color scale annotations, the labeling for the maximum and minimum and scanning of the results in the model, normalized deformation, and indeed mirroring of the results. We start with AutoCAD input. This import earlier time was available, so you could nicely import DXF, DWG file, but based on the geometry concept. So when you're dealing with the geometry concept, you're dealing with the interaction of these parts, shapes, and the tolerance between their intersections. However, we extended, and now you can also import the models based on the BRAP definition and associated topological data. So these information now can be imported into Dana, and it's very robust, and with respect to the accuracy, it become kind of independent with respect to the individual tolerances that each shapes and parts earlier time they had with respect to each other. So this is one of the good improvement that you can take benefit of, that especially for the 3D type of geometries that you want to import. With respect to the model modifications, so we incorporated and added the lofting feature. This lofting feature covers different settings, but long story short, it helps you to boost and upgrade your lower stream, or say the basic geometries, to the upper stream geometries. So here you can see I have two curves, and based on the loft, I can generate a surface in between, and I can proceed with the rest of the meshing and analysis in the model. In this slide, you can see different scenarios or some examples that this loft operation can help you to convert your optimal geometry to the solid, or say the upstream geometry in your analysis. So if you have two types of shapes at upper and lower part of the model, you can easily convert that to the solid. If you have a series of wires and reference lines, you can come with the kind of 3D shapes, and also in terms of the box girder and tapered shape, you can also take benefit of these type of features. If I want to be a little bit applied, I would like to go over one practical example. One of the challenging approaches is, for instance, to simulate or model in a parametric way double arch dam. The characteristics of this type of models is you have two different curvatures. One is from one side of abutment to another side, and another curvature is from top to bottom. So most of the engineers, they do have certain formula to create these parabolic curves, and they can generate these curves in upstream and downstream. So these things can be easily in a parametric way be generated. However, you can, from this point onward, you can take benefit of loft function that we have in Dana, and define your lower section and upper section surfaces, and proceed with the reference to the middle reference wire to come with the final solid geometry with complexity of the abutment or the connection surface with the abutment. So this is very practical, very nice tool that helps you, especially in terms of parametric approach, in terms of the speed of the modeling. You can easily use this option, and based on the series of parabolic curves, you can come with the final 3D shape. To continue, there is one option or tool, we call it joining wires. So if we have a series of lines, edges, curves, and these individual entities, by using joining wires operation, can be converted to the one wire. So you can see a series of 8 edges based on this operation can be merged to each other and become one wire. And if this wire is closed, you can directly convert this closed wire to a surface. So this is again another speed up process, especially if you have a series of segments and you want to basically convert them to some sort of continuity with the context of wire. On the other hand, if you have a continuous wire or edge, you can break, split, and divide it based on different tools and options that we have. This division can be identified based on the ratio, that you can define some sort of ratio along the length of your curve or edge. You can define explicit distance. You can divide it, or you can impose and define series of nodes, and then based on the projected position of these points, you can split your edge and curve. Another useful tool that we have introduced in this version from the Boolean operation family is cut shape. This cut shape helps you to interact and intersect different bodies, and also keep the common geometry shape for further manipulation in the model. So here in this particular case, you can see there is a cone, there is a sphere. So based on the reference target and tool, you can cut the operation, cut the model, and also keep different divisions in the model for further meshing or interaction, or say process in the modeling. This cut shape also has additional advantage if you have a sequential division in your model. For instance, you could have a tunnel like TBM tunnel with certain divisions for your lining, or in this particular case, you have a solid dam and there is a construction sequence that you want to define in elevation. What you need to do, you need to define the reference surfaces that you want to define or to be cut, and then as much as these surfaces have a little intersection with the reference or target shape, based on the cut shape, then automatically considers the continuation of the inner planar surface per reference surface, and you can easily divide your solid model. So you don't need to define all these cutting surfaces all the way through your solid bodies. This is very nice and optimal way of operation in the model. So we continue our presentation based on the geotechnical solutions. We have done significant developments, improvement and enhancement in our geotechnical solutions by introducing different wizards and also optimized workflows. Earlier time, we have introduced our wizard for the modeling pile, but we extended based on the new type of, say, direct integrated bending pile. Now it's available in 10.4. For sheet pile wall, we have different references for our profiles. These profiles can be addressed from the existing, say, profile library that we have in the installation in the Dyna, or you can define, as a user, define your own profile. But we have a couple of slides I touch bases, and then Jean-Claude gonna give a detailed live demo. For Anchor, there is very nice and integrated solution in terms of introducing the grouted part, in terms of introducing the bond slip behavior, the anchorage length, and all those things are defined in a one fully integrated environment. Definition of the water level or phreatic level became very easy in 2D and 3D based on the basically position that you have at the geometry. You can define the water level and go through the dewatering or release of the water and recall these water tables in the stage construction and consider the staggered analysis. Moreover, with respect to geotechnical solutions, we have introduced a new set of applied tutorials, so you can refer to them, you can use them to become acquainted with the workflow, and also utilize them based on the conventional or typical type of works for the geotechnical solutions. And to make it even more easier for you to rely and trust in our solutions, we have incorporated 2 additional verification reports. One is for the soil material model, which we have validated based on the other reference numerical results. And also for the pile model, we have validated based on the reference and analytical solutions. So you can also use these extra verification reports for extra assurance to proceed and incorporate data with your complex geotechnical applications. With respect to embedded elements, earlier time we have introduced this concept of embedded element as a context of reinforcement. We extended this concept by means of pile elements, and now in DNA 10.4, we are pleased to introduce this or use this concept of embedded feature for anchor and sheet piles. So you can use the sheet pile and anchor. I quickly go through the concept, but nicely you can follow that in the live demo. If you have a 2D type of analysis, you can define the sheet pile by means of line. And if you have a 3D model, you can define the sheet pile by means of a face. How it works, these 2 concepts are absolutely independent and mesh-free, so you do not need to worry about meshing a process for the sheet piles. They are carrying the concept of embedded element. You only need to go through the process of assigning the associated properties. If there is a interface definition, so there is a soil structure interaction, this interface can be automatically generated by use of one R factor that we can explain later. And when you want to go for initialization, when the interface and corresponding sheet piles are not active, the continuity in the soil layers are guaranteed, and you can nicely proceed with the stress initialization. And after activation of the sheet pile and the corresponding interface, you can proceed with the excavation setup in the program. When you deactivate the soil layers, for instance, you go through the level of excavation, then automatically also deactivate the loose or hanging interfaces. So in terms of data management, in terms of active, deactive, as a user, you're dealing with the minimal operation. For the anchors, also we have the same concept. We have a part which is a grouted and the free length. The grouted part also has a relation with the adjacent soil based on the bond sleep concept. The dialog box Jean-Claude going to show you, but briefly depends on the 2 types of elements. These elements are blend of concept of material model and geometrical information. Depending on type of the elements and the reference material, the type of interaction with the soil for the interface, you can introduce the sheet pile in the model. The basic concept is the sheet pile is confined with the soil, so literally is pressed by the soil from both sides. But if for your design you want to consider some sort of a tip failure, you can also activate the sheet pile wall tip in the model. The R factor is the reduction factor that can be used for if you want the soil parameters to be used for calculation of the clone friction type interface between the sheet pile and adjacent soil. If you click on load from library, then Dana automatically brings 2 types of profiles based on ArcelorMittal data that we have and incorporated in Dana based on the Z profile or U profile. You can choose one of these sections that you want based on the different available types. All the sectional properties automatically be driven. If you have for your own business, your own profile or your own specification, geometrical specification, no worries. You can write your own library and take benefit of that in your workflow. With respect to anchors, as I mentioned, the whole process and solution is very in one dialog box. You can just say what would be the length of the grouted part, what would be the material type, what would be the failure criteria that you want to consider for the grouted part, and in terms of the geometry, what are the characteristics for the, say, the diameter or the spacing between the anchors, and so on and so forth. So now I would like to hand over the session to Jean-Claude, and he's gonna present this process in a live demo. Jean-Claude, the session is yours.
Okay, thank you, Mazia.
But I think you need to confirm. Yeah, now we see that.
It's going. Hi everyone, my name is Jean-Claude Borel, and as Mazia mentioned, I'm going to highlight some of the geotech functionality that are related to sheet pile wall modeling, anchor modeling, definition of water level. And to do that, I'm going to use one of our case, which will be a tutorial available online in the coming days, which consists on a plane strain model with 3 different soil layers. For this material, for the material assigned to this soil layer, we use Moore-Coulomb model. Only the Young's modulus varies through the depth of this model. We will consider a couple of excavation level, 4 actually. And the idea is to build a sheet pile wall along this edge, and later on to define 3 anchors to associate 2 different water levels. First, we will start with a water level at -3 meters. And since we will be dewatering on the excavation side to up to -17.9 meters, we will create a second water level like a step function. And finally, we will go through the setup of construction stage analysis, and we'll look at some of the standard output that Diana offers. So to start with, I'm going to build the geometry of this sheet pile wall, which basically will just consist in a line. So I create a line that I call sheet pile wall. So starting point of my sheet pile wall is at the top here, and the end point is at -32 meters. And I just click create, and you can see that on the left side, on the geometry tree, under the shapes, I have a sheet pile wall geometry, which is highlighted in pink when I select it. Now we need to define some sheet pile wall set with properties. And to do that, I'm going to open the sheet pile wall wizard. So as Mazia quickly mentioned in the presentation, we have 2 types, the equivalent thickness cross-section and the generalized cross-section, which is based on the EI and EA parameter. And when you use a generalized cross-section type, you can also access to this predefined library of sheet wall cross-section. In today's exercise, I'm going to use the equivalent thickness cross-section. So I'm going to give it a name. I keep it simple. I call it sheet pile wall, and I'm going to create a material to define some property. So the class is sheet pile wall. I define a name. And in today's, I'm going to use the soil-derived column friction. It means that the properties of the interface, which will be created automatically between the soil and the sheet pile wall, will get their property from the surrounding soil. I won't include any pile tip. So here is the standard form with the different value that you need to specify. So I will consider a Young's modulus. So for today's demo, the value are not that important, although they are coming from a real benchmark. And I take a R factor, which is 0.8, which is a common value. And I click on Create. Now you can see that I have a new set under my geometry tree, which is a sheet pile wall. So what I need to do to basically assign the property of this set to my geometry, I can simply drag this geometry to the set. And of course, it's a live demo, so it's not. Yeah, it is. Okay. So now you see that my geometry is part of this set. And when I double click on it, you can see that on the right side, I have the property assigned. So you can just drag and drop the entity to the set, and then it will automatically assign the property to this set. Another way would have been to first create the sheet pile wall set and then the geometry. In that case, the last set which is created is the active one, and any entity or geometry that you then create would go directly to this set and carry the property. So there are different ways to do that. I mean, it's really depending on your mood and your preferences. So this is how you create a sheet pile wall. And as you can see, you can easily access all the properties through one window. And in 2 clicks, basically, you can define the sheet pile wall. Let's progress in the model. And I made a different model at different steps to save time and create some anchor. So this is, again, the model. This one, the sheet pile wall is there, so it's already created. Under the material tree, you can also see the sheet pile wall material that we have assigned. And now I'm going to create one anchor from this point and going down like this with an angle of 27 degrees. So first I create the geometry of this anchor. So I'm going to call it anchor top. And for the method, I'm going to use angle. The starting point will be this point. I want an angle of minus 27 degrees, for instance. And the length of this anchor, so the length of the anchor is the total length. It's the free length plus rotate part. I will consider 19.6 meters. And you see immediately on screen that the anchor appear with the right angle, and I click on Create. Then this geometry, this anchor top geometry appear under Shapes. The same way we did for the sheet pile wall, now I'm going to create a property set for this anchor using the anchor wizard. So I keep the same name, I call it anchor top. I'm going to define a bounded length of 8 meters. And I'm going to create a material. So I call it anchor because all my anchor, the 3 anchors will have the same material property, basically. Only their spacing will be different. So for this one, I'm going to put 2.17. And I'm going to define some stiffness parameter for the bounded part of the anchor. So 1.10, for instance, and 1.8. I don't consider any failure. For the geometry, I need to create a property. So I will make different property for the top anchor, the middle anchor, and the bottom anchor, because they will have different spacing, basically. So I create one for the anchor top. And here, for the input, you can choose between diameter and cross-section. I will use cross-section because that's the parameter I have. So it's 0.00115 square meter. And the spacing in this particular example, I will use 2.3 meter. And then I click create, and you see that I have a new set, which is anchor top, with anchor property which is created. So as I did for the sheet pile wall, I can simply select the anchor top and drag it to the set, and automatically the anchor geometry is assigned to this entity. And if I zoom and change the color of the anchor in black, and show the material of the anchor in black as well, you can see the grouted part, which is a little bit thicker, and the rest of the anchor for the freelance. So it's very intuitive and very simple. I mean, you through the anchor wizard, like we did for the sheet pile wall, you can specify all the property in terms of material and geometry, create the set, and drag and drop the entity or the geometry entity of your anchor to this set. The same way, I could have started by creating the anchor set, and then the geometry would have been assigned automatically. I can do that, for instance, for the second anchor. So I create a new anchor set, but I'm going to go anchor mid for the middle one. I will also consider an 8 meter grouted part for it. For the material, I use the same, and I'm going to create a new property because the spacing will be different. So again, I'm using cross section, and for the spacing, I take 1.35. So now I create the set. I have the set which is created, and then I create the geometry of the anchor. So I give the same name, anchor mid. Same way, starting point will be there. The length will be 23.3 meter, for instance. And again, I give it an angle of 27 degrees. And I click create. And you see that automatically the anchor appears under this set because this is the last active set. And automatically the property has been assigned. So that's why you see that the second anchor displays the grouted part and the free length. So there are two ways of working, and yeah, it's really up to the user to do the way he prefers, basically. So let's move on with this model. So this is the same model where basically I have already my 3 anchors available, and I'm going to define a pre-stress for this anchor. So I will start with the top one. So I call it anchor top with an associated set called anchor top as well. And I scroll down, and you have the anchor pre-stress force. Then I can select my top anchor, and I just apply the pre-stress. For this one, for instance, we apply 33,000 Newton, and I click create. I can repeat the same thing for the second anchor, the middle one. So I choose the middle one, and for this one, I apply 700,000. Great. So this is the way you can assign a pre-stress to your anchor. So it's very easy and very intuitive. So let's continue. I have prepared another model where I've already defined my 3 anchor forces. The The anchor are defined, the sheet wall is defined. I have also included some boundary condition. Here is a symmetry condition. You can imagine that yeah, we are just modeling half of the model. And what I want to show you now is how to include water level in your model. As I said in introduction, we will consider starting with a water level which is around -3 meters. Then we will be dewatering on the excavation part up to -17.9 meters. So for that, I need to define 2 water levels. So I start with one. This first one, I'm going to call it groundwater -3 meters, for instance. I give it the same name for the set. I select the model and I define a function which will consist in 2 points. So from 0, I start with -3 meters. And the length of my model, the x dimension is 120 meters. So I also consider -3 meters of water. Okay, and click create. And now I hope you can see there is a water table, a water which is defined and which is represented with a blue line with this water sign on the model. And you can also find under the geometry tree the water level here, under water levels. So I'm going to make another one, which is the varying water, which I call -17.9 meters. And these 2 water levels, we will use them in the stage construction for the dewatering. So again, I select the whole model. And here, the function is a little bit more elaborated. So I start at -17.9. Up to 30 meters is also -17.9. And then I have a jump to 3 meters and -3 meters. So this is the part where we are going to excavate and where we dewater. And this is a -3 meter level. And I click create. The table is created. And if I add the -3 meters, you see now that I have a water level varying from -3 meters to -17.9 meters. So as you see, it's very intuitive, and there's no real difficulty to create this type of water level with a step function or variation. So the model is almost complete. I already prepared a full model with the mesh, so we can check that all the anchors have been meshed. We have the difference part of our soil, so the 4 excavation layers, then the rest of the soil layers, and the sheet pile. We can also go through the material for the sand layers, the anchor, and the sheet pile wall. The boundary condition are there. The loads, the different anchor loads are there, and the water level. So everything is ready. So the next step basically is to set up the analysis. And for this case, we are going to use the stage construction, which can be seen as a simplified version of our very well-known phase analysis. So this one is more oriented for geotech. And basically, I'm just going to define a couple of phases, and then I will move to a next window where I define the complete model. So I first define a stage that I'm going to call the initialization one. And by clicking on active part of the model, you can see all the models, part of the model that you can activate and deactivate. So the first thing is water, and I'm going to specify the water level. So we start with -3 meters. We initialize stress in the new elements. For this initialization phase, only the soil parts are active, so the sheet wall is deactivated. Anchor, mid, and top anchor are also deactivated. And as you can see, there's no interface sets. This is also something we could see from the mesh tree. As Maziar mentioned during the presentation, the interface between the sheet pile wall and the soils, as well as the interface for between the graphic part of the anchor and the soil, are automatically created. So only the Dyna kernel deals with it. You don't see them. So you don't need to worry about their activation or deactivation. This is fully automatic. So for the first phase, basically, I only consider the soil part as active and a water level of -3 meters. Now I can move to the second stage. I will use the duplicate function. So it will just duplicate this phase, and I'm going to rename it. I call it placing sheet pile wall and dewatering, for instance. So it carries the property of the previous phase, but I'm going to change that. So I want to dewater to -7.9 meters. I don't need to initialize stress in new elements. And the only set which will be activated during this phase is the sheet pile wall. I can go on like this, duplicate, and make the first excavation, for instance. Excavation 1. So we keep the water level at -17.9, and we basically remove the excava 1 set. In the next stage, I'm going to activate my first anchor. So I call it placing and loading anchor, for instance. Without typo, it would be better. And I initialize stress because I'm going to pre-stress the anchor. So I need to activate my anchor top. And I go to the load tab, and here I need to apply the anchor pre-stress, which is name anchor top. And that's it. So we can go on like this with the different excavation phase and the placing of the different anchor. I have already prepared the model with the complete settings. So let's see the different phase. So in the previous window, we were at this stage where I place the anchor top and I activate the pre-stress. Then I make a second excavation where I remove the excavation to the soil layer. Then I activate my second anchor and I apply the pre-stress. Next, I excavate further, put the final and last anchor with its associated pre-stress, and then the first excavation layer. So the analysis setup is complete. I already performed the analysis to save time so that we can look at some of the default result, because I did, as you could see, I didn't specify any specific setting for the output. So all what we have here are default Dyna output for the soil layer, for the sheet pile wall, the anchor. So we can start maybe by looking at the pressure head to see the dewatering between the initialization phase and the second phase. So here you see that we have 97, so it means that we are at -3 meters. And if I move to the next phase where I dewater without a deform, you can see that there is a jump. So the dewatering is applied. We can look at the deformation of the whole model, for instance, through the different phase. So I start with the initialization phase, so there's nothing. And I move on. But instead of doing that manually, we can eventually make an animation and go through the results. So you see the variation through the different stage of our analysis. Animations are always nice and better than long speech, I would say. So let's go until the end. Next, we can look at some sheet pile wall results. For instance, so all the output you see there are default output when you have sheet pile wall results. So you have access to pressure head, total head, the interface relative displacement, the stresses, the forces, the moment, the traction, the pore pressure. I'm going to look at the distributed moment, for instance, and I'm going to show a line diagram. I'm going to zoom in, and again, I can go through the animation and see the variation of this bending through the different phase. And you see the placing of the anchor as well. We can challenge a little bit more the program. And what we have done so far is basically we only model half of our model, and we can show some mirroring results. If I go to mirror, enable mirroring. This is a little bit too much. Mirror. So here is basically the full model. And again, we can make the same animation. Let me zoom in a little bit and scan the bending moments through the different phase. I'm going to leave the animation and start from scratch. Starting with the placing of the first anchor. So I'm going to disable mirroring. So this is the placing of our anchor with the applied pre-stressing. Then we excavate further. Then we place the second anchor. Again, we see the applied pre-stress. Further excavation and the placing of the last anchor, and then the last excavation. So as you can see, I mean, setting up such a model is not that complicated because we have made available some intuitive tools like the sheet pile wall wizard, the anchored wizard. The water level definition is also very simple, and making all these phases through the construction stage is also very intuitive. You can easily activate and deactivate the mesh sets and activate anchors and sheet pile wall. And with the large variety of results output that we have, you can really scan your model and get a good understanding of the behavior. So this is it for this short presentation about the Geotech feature. This will be discussed in more detail in a webinar in 2 weeks' time, where we will go through this complete case from A to Z, basically, and hopefully this will be of interest for you. So Mazia, if you want to take over, it's all yours.
Thank you, Jean-Claude. So now you should be able to see my screen. So I continue the presentation based on the remaining features, a little bit speed up to make sure that we could catch up to cover all the items. Among other developments and enhancements that we can also touch bases of the naming of the load combination. This was also another important request to have more control from the end user during the activation, controlling of the load associated to the design, so user can specify their own name and call them during the analysis. Another improvement that we have done is the synchronization of the geometry basically dialog box and the working environment. And also we have introduced a nice and interactive selection filter. So that means from the working window, if you select any geometry shapes or any object, the corresponding parts and items will be highlighted in the geometry window, and other way around. And if your model is composed of series of shapes and or elements or nodes or sets based on the corresponding filter, you can easily highlight and select those specific items or sets that you are looking for. Map mesh. This is very important from the user point of view, especially when you're dealing with some nonlinear analysis. The stress field and smoothness of this distribution of the stress field is very essential. So most of the engineers and users want to have a nice, uniform and structured elements. So the necessity of that is using the map mesh. In earlier version, we had this map mesh based on the 4 edges. So your geometry somehow should be bounded to the 4 edges, and 2 by 2 you should always correlate with each other. However, in the new version, this restriction has been removed, and you can use the map measure when your model consists of more than 4 edges. So now you can see there is a 1 arch here, there are 2 arches on the top and 2 on the side. So again, now in 10.4, you can take benefit of our new and enhanced map measure to come with a nicely patterned and smooth distribution of the elements in your model. There are some reference and anchor points that help you to basically guide and control your map mesh. These are some of the examples, so you can see when your model consists of several edges based on the reference points, you can generate a very nice distributed and structured map mesh for your model. Another request that was important, and that was the definition of the clashing shape. So what's the meaning of that? Usually when you had an embedded element, it was important from user to allocate these embedded to the specific set of mother elements. So you have, for instance, in this example, you have a soil layer, you have a concrete foundation based on the plate, and you assign the grid reinforcement to that plate as embedded element. However, you want to emphasize and restrict the program to only consider this grid reinforcement to the concrete slab and do not consider any contribution to the soil. So using the option of this clashing, you can say exception or exclude this contribution except soil. So this way you can control, if you have different say embedded elements, which element is belong to which mother element. So you have this extra control. For the output, most of the time, for instance, for the flow or say heat flow or flux or discharge, you have a series of nodes that you want to get the output for that particular node groups or node sets. So it was a bit cumbersome if you wanted to select them one by one at the mesh level. So now in 10.4, we made it available at the geometry level. You select the surfaces or the edges or the part of the model that you want to be say it in terms of the data management, to be stored all the associated nodes that later in the post-processing you could easily recall them and get the results for those particular sets. The incremental mesh system is a very powerful tool. This is a very important tool, especially when you're dealing with the complex and large models. And when you mesh this model, it may take some time, but all of a sudden you realize, oh, the client is asking some modification at a certain part of the geometry. So you don't want to go for the meshing the whole model. This incremental meshing, it only goes through the meshing at the modified area or zone and adjacent affected area in the model. So this is very powerful. We extend that with the basically incremental meshing. Now also it's considering the reinforcement and pile. So if you want to remesh the model, now it doesn't go for the remeshing the whole embedded pile or embedded reinforcement or grid. It only goes for the certain localized and affected area. As an example, in this complex structure, we have about 3,400 shapes, which more than 2,400 of them are reinforcement. If you go for meshing, it's going to take something about 10-15 minutes. And if you want to remesh it, you see it within 2 minutes, everything go through. So it's very optimal and very useful operation that helps you to speed up your modeling and optimize your analysis process. There are additional icons and operation and tools are available. One is to identify the nodes and elements with corresponding IDs in the model. So you have identification for the nodes or for the elements. Then you can easily see those highlighted nodes and elements with the corresponding labels in the model. Moving forward, this tool can be used to identify the co-located points. So if you have a model and you have some discontinuity in the model due to definition of the interface or a fault, or maybe you just split, you introduce discontinuity between different parts. So you can easily identify this discontinuity by means of coincident nodes in the model at the mesh level. The tooltip pointer also is a very useful tool in a kind of a quick overview for the model. By activating this tool and hovering over the model, as your mouse goes over each of these shapes, automatically a summary of the attributes that have been assigned to these geometry will be listed for your quick check. So moving forward at the analysis level and kernel level, we have done a tremendous job. It's a huge job we have done. There are lots of optimization, enhancement, improvement with the formulation. At the material level and constitutive levels, there are lots of improvements and additional capabilities are available based on the model code or to the existing constitutive models. However, I just highlight some of the things, but the detail of them also available in our online manual and the release notes section. One of the new developments or the extension is introducing the hydrostatic pressure load, and now you can assign that to the flat shell in conjunction with the infinite axisymmetric and curved shell. Prescribed velocity load can be introduced into the model when you're doing the transient dynamic analysis by means of you need to support the nodes or constrain the degrees of freedom of the certain nodes that you want to these velocity loads get imposed. If this velocity load is not active, then this constraint of the DOF will take place. Therefore, you will have a zero displacement. For base excitation, earlier we had acceleration input, but we extended now user can define the velocity input. This velocity input is very useful, especially if you have some readings and records that you can directly input that, and you can introduce this base excitation and rigid body motion in 3 orthogonal directions. For modified camclate, there is a porosity update, or you can keep it constant or make the process get updated through the dialog box in the corresponding material model. For hardening soil model, modified Morclum, we have done lots of extension beside of the controlling the shape of the cap and additional parameters that help you to basically nail the results. You can use this material in conjunction with the strength reduction method, not only with the reduction of cohesion friction angle, also with the combination of the cohesion and friction angle. So there are 3 scenarios can be introduced into the model for performing strength reduction analysis. Pre-filled elements, this is very important and useful feature to literally reduce your domain, your infinite domain into the finite domain. So how it works is basically used to simulate the absorbing boundary in the soil column and transfer the load and the force from the infinite zone to the from the finite zone to the infinite zone. In the 2D definition, there is a line, and in the 3D definition, there is a phase. And attribute of these type of free field elements can be automatically driven from the adjacent soil. This is a very powerful tool, and in the next slide I will tell you that when you combine this with the absorbing bottom boundary, especially when you're doing the earthquake analysis, you need to have some sort of non-reflecting boundaries at the bottom of the model. In the end, these type of boundaries work like normal support if you do the static analysis, but it automatically converts to the viscous dampers when you want to conduct some sort of a dynamic or transient analysis. So I would like to refer to one of the benchmark tests, the 15 International ICOR benchmark test. This is a very nice example and classical example that you can find it online and refer to that, and you can see how with Diana you can capture the perfect simulation, and this is a comparison of that with the, say, some actual readings, so how simulation can predict the actual readings. Further on, for structural nonlinear analysis and combination of with string reduction method, as I mentioned, most of the clients now they do this type of check to consider the stability of the overall of the model, while the part of the site goes for the construction, or maybe there is an earthquake and they want to see if the model remains stable when the earthquake is happening. So therefore, now you can combine your string reduction method and structural nonlinear analysis sequentially or after several steps. So it's up to you, and you can assess and evaluate the factor of safety of your model at any stage of your analysis. Another important feature is our analysis progressive window. This window is very useful, it's informative. As you perform nonlinear analysis or stage construction analysis, you can easily identify at which level of the stage you're, what level of load steps you're, how many increments you're advancing, what's the convergence, how many steps are converged, how many not converged. So in a one dialog box or window, you can get tons of information, useful information, to predict and monitor the rate of convergence for your nonlinear analysis. So I would like to hand over the session to Chantal to give you insight about our design features. Chantal, session is yours.
Thank you, Maziar. My name is Chantal Frisse, and I will present the new features in the design application. First, I want to start with the anchoring length of the reinforcement. There's a development length needed to embed the reinforcement into the concrete to establish a safe bond between the concrete and the reinforcement. So this anchoring length can be entered in Diana. And as you can see over here, that you have to enter this anchoring length at the beginning and at the end. And for reinforcement grids, you can see that we do it in both directions, in both local directions, so in X and Y direction. This anchoring length results in an applied reduction in the embedded reinforcement bars or grids in the Young's modulus, but also in the cross-section area for the reinforcement bar and the equivalent thickness for the grids. This reduction is linear over the anchoring length until 0 at the end or the beginning. So here you see the Young's modulus plotted on a reinforcement grid. The local axis of the reinforcements is the same as the global directions. So here you can see in this figure that the full Young's modulus value is still there in the red area, but at the beginning, this is the beginning size of the grid, that at the begin a larger anchoring length is entered than at the end. And here you see the Young's modulus in the local y direction of the reinforcement grid, and you can see now that only in the y direction an anchoring length is entered in the beginning and not at the end. This anchoring length can be accounted in a design, linear, and in a nonlinear analysis. For example, this reduction of this Young's modulus and this cross-section has an effect on the calculated bending moment capacities in the design calculation. That's what you can see over here in this graph. Here you see that the capacity as a function of your location in the anchoring length is reducing at the end towards 0. For reinforcement bar, you only have to enter the anchored length at the beginning of the end. And here you can see that this is the beginning of the bar. So here you have a smaller anchoring length than at the end. In Diana 10.3, in the design application, you could already calculate the bending moment capacity and shear capacity. But this was only available for cross-sections in curved shell elements or with solid elements in combination with composed surface elements, and only with reinforcement grids. Now we made it available that the calculation of the capacity is also available for composed line elements. This makes it much more flexible in application. Now you can analyze all shapes of constructions, like for example the box girder beam. You can use grids, you can use bars or both, and all the results of the capacity are plotted on the line. These capacities are not only available in the design application, but also in the nonlinear calculation. The capacity are depending on the normal force, the membrane force. So in every step in the nonlinear calculation, these membrane forces will be calculated and with the corresponding capacity. So now, even in a nonlinear calculation, you can see in every step how far you are from failure. Now you can see that we have in Diana the capacity calculated in both surfaces and in composed lines, which you can see over here in the result browser. For the surfaces, we have 4 capacity results, and that is related to the XX and YY, exactly the same as like the curved shell elements. So a moment MRD, the RD is for resistant design, XX plus is a positive bending moment around its local Y direction. A positive bending moment means that it has tension at the positive side. With the corresponding capacity moment, we also calculate the pressure thickness. So if you have a positive, so an MRD XS plus, you have tension at the positive side, so you end up with a pressure thickness or a pressure height at the bottom side. So a plus and a minus sign behind it, you know it is a positive or a negative value. For the composed lines, it is related to a line. So it's related to the cross section in ZY cross section. So now you have the subscripts Y and Z. So a moment MRD Y plus is now a moment around the local Y axis. But how are these bending moment capacity calculated in the composed line? What we do is that we divide the cross section into 100 layers. And for every layer, the width will be calculated. So here, for example, you see the box girder beam. And if you look at the width, then you see that it is becoming an I-shaped. So the thickness here in the middle of the beam is equal to the width of the both webs together. For the Eurocode method, we assume that we have a 3.5 per mil compression strain at the extreme fiber. And then with an iterative procedure is applied to calculate the pressure height in such a way that you have equilibrium. Therefore, we use a bilinear stress-strain relation to get the forces that should be in equilibrium. The concrete cannot resist any tension, it's only compression. And of course, the bars and grids are considered as well and will be checked on every location if it's yielding, yes or no. And if you know all these forces, out of these forces in the location, you can calculate the bending moment, and that is the moment capacity. There are two methods in Diana 10.4 for calculating this bending moment capacity. The first one is the Eurocode, like I showed you in the previous slide. So it's really based on the bilinear stress-strain curve with no tension. But there's also a second method available, that's we call the total strain curve, which uses the real total strain curve that you have applied to the concrete. So for both tension and compression. Now we don't know when the ultimate bending moment occur, at which strain at the extreme fiber. So what we do is we increase the curvature and calculate for every curvature the bending moment, and we keep track of the maximum value. In Diana 10.4, it is also now possible to use and model reinforcement bars in the calculation of the capacity for shell elements and composed surface elements. Previous only grids were considered, but this new feature makes it much more flexible in application. So the reinforcement bar only contributes to the elements where it's in. So here you see a plate, but at the bottom there are 5 reinforcement bars. So we get a very high capacity in the elements where there are the reinforcement bars, and in between where there is no reinforcement, you have a capacity of 0. Of course, we can average the results in Diana. So if the bars are placed in a regular spacing, like in this example, we can average the results over the spacing distance, and then you get exactly the same results if you have modeled it with grid reinforcement instead of separate bars. As I just told you, that the capacity are depending on the normal force, the membrane force. So it is very important to take this normal force into account in the calculation of the bending moment capacity. In the nonlinear calculation, it's calculated automatically in every step out of the membrane forces. But in the design application, you have to define a pre-stress load case for this. For example, what you can see over here is a column. So the self weight and the top load has a big effect on the bending moment capacity. So you really have to take this into account. Here you can see the capacity that the capacity at the top is much lower than the capacity at the bottom, where you have a much higher normal force. The pre-stressed tendons are also a special case, what you can use in Diana 10.4 in the calculation of the bending moment capacity. In this case, the initial strain here is the reinforcement tendon. This is just a regular reinforcement. But in this reinforcement tendon, you can see that the initial strain and stresses in the pre-stressed tendon are taken into account. So not only the initial stresses and strain are important of this pre-stressed tendon, also the location, of course, is very important of this pre-stressed tendon. So here you see, for example, a beam with two spans and a curved pre-stressed tendon. So if you use the pre-stress as the load case for the calculation of the bending capacity, you can see now that you have extra very high negative capacities in the middle of the span and very high positive capacity at the supports. There's another new feature in design, and that is about the calculation of the crack width in serviceability level state. This is a kind of backwards capacity calculation. So now we know the reinforcement moments and normal force out of the load case or a load combination. And we have to calculate the strain at the location of the reinforcements which correspond with this bending moment and normal force. So in Diana, we implemented the Eurocode formula for that, in which the strain at the location of a reinforcement will be reduced with the average strain in the concrete between the cracks. And this strain will be multiplied with the maximum distance between the cracks. This maximum distance between the crack can be entered in Diana. If you don't specify any value, Diana automatically calculates this value. And you have to enter 4 values for the positive and negative sides in both directions. In Y, this is a surface, so in X and Y direction. If you don't entering, it's automatically calculated, but you can also overrule this value by just entering it yourself. And as you can see, the results, the outcome is the maximum crack width in the steel in SLS for the surface. So here you can see that is the crack width in XX plus and minus in XX and YY. You can also check the maximum distance between the cracks. So this is this value that's automatically calculated. You can also view this as a result to see if it's correct. Here you see, for example, just a beam and with just one span, and it is loaded with a pressure on the top surfaces. So this beam is going to bend, and you see that the crack width corresponds with the reinforcement bending moment. So the largest values of the crack is at the mid of the span. This new crack width check and result is available not only for these surfaces, so for shell elements and composed surface elements, but also for composed line elements. In Diana, in the design method, design application, we can also average results. So you do not have to design your construction on local peak values. And there are several ways, methods implemented in Diana for the averaging. And here you can see the circle around elements. So that is explained in this picture. So the circle is created around each element, and it is seen which is crossing the spreading line, the average line, where you have to average the results. So which part of the line is cutting and has within the circle contributes to the averaging. So the averaging is weighted on the length in the circle. You can imagine that this method of averaging is not that accurate in very irregular meshes. So that's why we implemented two other methods, the circle smaller radius. That is exactly the same method, but not a circle around a complete element, but then the circle has the same area as the element itself. But the last method, the intersection spread line, is of course the most accurate one, because there this determined exactly the intersection of the spread line and the edges of the elements. So every element contributes to the average value in proportion to the real or relative length of the average length. In Diana, you have to enter the spreading line as a factor of the thickness. And in Diana, you can also shift the results. And there we implemented the two methods, the circle round element and the intersection spread line. In Diana, we can also have a nice feature. We call it normative loading. And it calculates the maximum and minimum reinforcement moments and shear forces for all load cases, load combinations, envelopes automatically. And it's calculating the worst load case scenario for the constructions. What you have to do for this is that you only have to define your separate load cases and classify the load cases if it will be a permanent load or a variable load, and this variable load can be dominant or a secondary, or it is a unique load. For the traffic loads, we do something special. For the traffic loads, you have to define sets. And a traffic load consists of a set with a tandem system. So that's a mobile load that is moving over your constructions and can take place and located on several locations. And the traffic load can also consist of a uniform distributed load. So here you see, for example, an example of a traffic load set for a carriageway width of 3 lanes. And you see that the first lane has the heaviest loaded lane with the heaviest tandem system on it. But of course, you can define in Diana several traffic sets. So for example, you can also make traffic sets for the heaviest tandem system in lane number 2 or in lane number 3. The last step of the normative loading is to define a combination of envelopes in which you define the load factors and from the different load classes. So you can just define just one combination of envelopes or multiple. And in this case, this has the advantage that you can calculate, for example, equation 610A and 610B equations out of the Eurocode just in one calculation. So then automatically, Diana calculates all load combinations, all envelopes, and calculate the worst critical loaded condition, which results in the maximum and minimum values for the reinforcement forces and moments in your construction. So I want to show this on an example of a bridge deck modeled with solid elements with composed surface elements. And we use the normative loading to calculate the maximum and minimum values of the reinforcement moments and shear forces. And if we divide the extreme values of due to the loads by the capacities, you will end up with unity checks. And these unity checks are also available in Diana. So when you plot these unity checks, for example, here from the moments and here from the shear forces, you can easily check if the construction is well designed, if the construction can resist the loading. If the unity check is lower than 1, then the construction is okay. So in this case, this bridge was well designed. The last feature of design I want to show you is the external forces output results in combination of the normative loading. Because normative loading automatically calculates all load combination envelopes and so on. But with which load combination and which position of the tandem scissors causes these extreme values? So these results can be visualized with these external forces. So per results of the normative loading, so the reinforcement moments maximum and minimum in two directions and the shear forces, for every result, you can see what is the worst case scenario and for this tandem system or for this UDL load case. So now you can use this load case for example, for a required extra nonlinear calculation. This was all about the design application. We already made some tutorials available on design where you can look in more detail how it works. But now I will turn it over to Maziar again.
Thank you, Chantal. So now you should see my screen. Perfect. I continue with post-processing features. We have incorporated and introduced new output items under the strain. We have introduced weighted crack width. This output is useful, especially if you have some sort of topological restriction for the element shape. So this helps for normalizing that effect of the strain localization. Under the stress output items, we do have the concentrated and distributed forces and moment, not only as a combination between element and reinforcement, also as a individual output. These outputs also are available for the beam, infinite shells, and other types of elements. For mixture analysis, you can introduce the permeability as a function of the saturation or the porosity, and you can get output the actual value that gets used into the analysis. And also, depending on the type of model that you have, isotropic or orthotropic, you can get different output parameters. And as a design output, we have introduced three different items for the model parameters. One is applied cross-section. For the reinforcement bar, we have the equivalent thickness for the embedded reinforcement grid, and also the reduction of Young modulus when the reinforcement for the reinforcement when the model is subject to the anchor loss. The change of thickness also is another output that now is available in Dana 10.4. When the model goes under the deformation, the thickness of the reinforcement or the bars can be changed. The flux output, now you can easily select a group of element sets, the associated nodes, you can highlight them, and it doesn't matter you're dealing with the heat flow or groundwater flow. Any type of, energy or fluid output can be measured through these nodes associated to those elements per unit of time. In terms of the post-processing visualization, we have introduced the color scaling annotation, so you can see the percentage of the distribution of the results in the model. You can easily highlight and tag where is the maximum results, where is the minimum results, and what's the value of that. So if you have your set is available, your output is selected, you can also take benefit of this feature in your post-processing to identify the critical parts in the model. There is a boundary edge display. So if you have a cutting plane, so when you cut your model, you can easily see the distinct edge for your plate of cutting. For vector plot arrow, now these arrows can be controlled, or the vector tail or head can be controlled to be allocated at the point or at the nodal position with respect to the elements. So it should be tail or head of these vectors. And also there is a normalized and relative displacement that can be identified, and the deformed shape can be shown in the model separately. The nodal averaging is available. This nodal averaging is available in the post-processing with respect to the mesh set. So in this particular example, you can see there are two sets are available. If you perform the analysis and you get the stress results, you can get the stress results in this mesh set independent with respect to this. And you can make the averaging per set. So now you see how these staircase results now became smooth in this particular case. And similarly for here, you can see in this mesh set how the result became smooth, and you can do this averaging over the whole model. Now you can see the transition of the stress between two sets. The mirroring is very powerful with respect to the mirroring plane. If you have a symmetric model, this symmetry could be quarter symmetry. So you can set up the model and perform the quarter symmetry analysis. It's much faster, but in the post-processing, you can nicely present the results in a full scale. And also you can take advantage of this, as Jean-Claude showed you in the live demo. You can also use this feature to show your model, a complete model at the mesh, and also geometry. So this is very powerful. You model a quarter, you go for the analysis, but for the reporting, you can show a complete set of model. And at the end, for the documentation, as I mentioned, we have 3 verification reports in total, 2 of them for the geotechnical. One is the comparison of the nonlinear soil model. Another one is the validation of the pile behavior with analytical results. And the last one is the classical reinforced concrete beam benchmark test with respect to the experimental results. So this brings us to the end of this webinar. Thank you very much and have a very good day.